Welcome to Day 8, Arc Length and Angle Relation. Today we will learn about the formula theta equal to S over R. Here are the supplies you will need. Remember to the earlier lecture that we found out there was a relationship between the measure of a central angle and the arc it intercepted. And what we found is that we could find the measure of that central angle in radians if we took the length of the arc and divided it by the length of the radius. Remember our example, we had a circle with radius r, and we had an arc with the same length r that was intercepted by 2 radii. What we found is that the angle created, theta, would be equal to the measure of 1 radian. Now this is fair and well enough, but what happens if we have an arc that is less than the length of a radius or greater than the length of a radius? How can we figure out the measure? Simply put, we're going to use the formula theta is equal to S over R. Well, what does this mean? Let's decipher the parts. Theta is the measure of the central angle given to us in radians, not degrees, in radians. So if it asks for degrees, you're going to have to convert. S is the length of the arc that's intercepted by the radii, usually given in some unit measure. R is the measure of the length of the radius, usually given in the same unit measure as our arc length. So we see that the value of the angle is equal to the length of the arc divided by the length of the radius. In example 1, we're given a problem where we're told to find the length of a radius of a circle given the measure of a central angle and the length of the arc it intercepts. Seems like a perfect opportunity to use our formula. Let's start by drawing the circle, and we know that we're given a central angle, so let's draw that as well. I'm going to write down my formula right away so I don't forget. Theta is equal to S over R. Remember that this problem is asking us to find the number of centimeters in the radius of the circle. Well, what part of the formula does that ask us to find? Obviously, it's the radius. That means we're going to need the other two parts, the measure of the central angle and the length of the arc, to find R. Let's start by finding the measure of the central angle. Well, in the problem it tells us that theta is going to be equal to 1.5 radians. Next I'm going to need the length of my arc, S. Well, that's also given to me as 6 centimeters. So I know that my unit is going to be in centimeters. In other words, radius will eventually be in centimeters. I simply now substitute in my values, 1.5 for theta, S for 6. I place 1.5 over 1 and then cross multiply. Now I have 1.5 times R is equal to 6, and I simply divide out the 1.5 to get a value for R equal to 4. Simple enough, right? In example 2, I'm given the length of a pendulum of a clock as it swings through an arc. I'm asked to do two things: find the angle in which the pendulum swings in radians, and then find that angle in degrees to the nearest degree. Well, as always, with these problems I suggest that you start by doing what? That's right, draw the picture. Well, here's the arc through which the pendulum swings, and here comes the pendulum. It's got a little circle at the end, little pendulum weight, kind of like a grandfather clock. And I'm going to mark out the other side where the pendulum stops swinging. So, in A, I'm asked to find the angle in which the pendulum swings. Remember, this is going to be the theta created between those 2 radii. So I use my formula, theta equal to S over R. I'm looking for theta, so I'm going to need to find the values of S and R. The radius is simple enough. This is the length of the pendulum, here given as 20 centimeters, which I label. The length of the arc is also given as 50 centimeters, which I also label. Now I simply substitute theta equal to 50 over 20. I plug this into my calculator and I get a value of theta equal to 2.5. Remember, this is 2.5 radians. This formula will always give you a measure of your central angle in radians. Now, in B, I am asked to find the same angle in degrees. So I will take my theta, 2.5 radians, and convert it to degrees by using my conversion factor. In other words, I'm going to multiply 2.5 over 1 by 180 over pi. Now I can rewrite this fraction as 2.5 times 180 over pi. I know what you're saying. Oh no, I'm supposed to be in degrees. I should have no pi. It should be an exact number. Don't panic. Multiply your numerator first. 2.5 times 180, you should get a value of 450 as shown on the calculator here. Afterwards, you have 450 divided by pi. Make sure your calculator is in degree mode, and then simply divide 450 by pi. You should get a decimal answer equal to 1.43 and some decimals. If you round to the nearest degree, theta will be equal to 143 degrees. And we're done. In example 3, we're given two closely linked problems. First, we want to find how many degrees does a minute hand go through on a clock in 45 minutes. Second, we want to know how many radians does it go through in that same amount of time. As always, I say start by drawing a picture. Here's my clock, and here are the 45 minutes that the minute hand would go through. Notice it looks like it's going around the circle 3/4 of a turn. Now, we want to know how many degrees are in that 45-minute turn. Don't confuse the minutes that you have with degree mode with the minutes on a clock. For this problem in A, all you really need to do is have a proportion of minutes versus degrees. We know that we are turning 45 minutes out of 60 minutes, and we want to know how many degrees are in that same turn. Well, one turn around the clock is equal to 360 degrees. Now we simply cross multiply. We divide both sides by 60 to get that unknown degree amount alone, plug it into our calculator, and we should get a value for x equal to 270 degrees. In other words, the minute hand goes through 270 degrees of rotation in 45 minutes, and visually this makes sense as well. If you were to draw your 4 quadrants with 0 at the top, you know that each quadrant gives you 90 degrees. So if it goes 3/4 of the way around, it would make 270 degree rotation. Now in part B, we're asked to find that same rotation not in degrees but in radians. So all we're going to do is convert our 270 degrees to radians by using our conversion factor. In other words, I take 270 degrees over 1 and multiply by pi over 180 degrees. Remember that I can rewrite this as two fractions, 270 over 180 times pi over 1. Now all I have to do is deal with that first fraction. I plug it into my calculator, 270 divided by 180, and I come out to a value of 1.5. At this point, I could write my solution as 1.5 times pi. However, it is also equivalent to write this in terms of a fraction. To do that, all I do is use the fraction function on my calculator for my answer, and I get a value of 3 over 2 multiplied by my pi, giving an answer of 3 pi over 2. Example 4 is a little bit of review. Now, we had done this problem earlier on a few days, but some people are still having trouble, so we're going to go over it. We're given a point, P, for -5, on the terminal side of theta in a standard position. We want to find the exact value of the 6 trigonometric functions for theta given this point. Well, let's first label where our point is. The x value is 4, so we come over 4. The y value is -5. That means we're going to come down 5 points. I draw and label my point, and this gives me a side from the x-axis to my point that comes down at a right angle. I can then draw the hypotenuse to the central point or the origin. My theta is now the reference angle between the terminal side and the x-axis. I know that my adjacent side is going to be 4, and my opposite side is going to be -5, And to find my hypotenuse, I simply use Pythagorean theorem as is shown here. I should get a hypotenuse value equal to radical 41. Now I'll label the sides of my triangle opposite adjacent hypotenuse in reference to my angle theta. Now I have three sides, I have a reference angle, I should be able to use my trigonometric functions. If you have not memorized these yet, use the mnemonic SOHCAHTOA, sine opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite over adjacent. This will allow you to find the given ratios as will be posted here. Next, we need to find the three reciprocal ratios. Remember, these are cosecant of theta, secant of theta, and cotangent of theta, which are simply the flipped values of sine theta, cosine theta, and tangent of theta. Finally, what we have to do is take care of any radicals in the denominator. In sine and cosine, we have to multiply here by radical 41 in the denominator so that the radical appears only in the numerator. Here are the skills that you should be able to do after watching today's video. If you're still having trouble, please go back and watch the different parts. Until next time, this is Mr. Mackman signing off.